Hi everyone, this video is going to go over chemical bonding. So we're going to talk about the different types of bonds, how they form, the elements in them, practice identifying bonds as well based on the types of elements inside them, as well as the electronegativity differences you see. So first of all, let's talk about why bonding even happens. So atoms bond to become stable. Atoms alone a lot of times are unstable. For example, if you have sodium, Na, just pure sodium, that lights water on fire. That's not stable. Chlorine, Cl, chlorine gas is poisonous, but on their own, these really volatile things, we put them together and now they're stable. So atoms want to become stable. And part of that stability that they want, that's having 8 valence electrons. And that's called the octet rule. If you remember from last unit, this is the octet rule. They really want to have those 8 valence electrons to become stable. So a little poetry for us here, a little simile. Chemical bonding is like the glue that holds atoms together. So chemical bonding is what holds our atoms together. So if you have that sodium and the chlorine and sodium chloride, that chemical bonding is what's holding it together. And there are 3 types of chemical bonds that you are going to see. Number 1, we have ionic. 2 is covalent, although covalent can really be broken into its own 2 categories, which would be polar covalent and non-polar covalent. We'll talk more about that later. And the 3rd type is a metallic bond. So we have ionic bonds, covalent bonds, and metallic bonds. So we're going to put all of these bonds in a chart to help us organize all of them, and so that you will be able to easily see the differences between ionic, covalent, and metallic bonds. So go ahead, jot down that at the top of your table, and we're going to talk through each of these and how they form. Up first, we have an ionic bond. So ionic bonds are formed by the transfer of electrons. So electrons are transferred. This means an electron goes from one atom to another. It leaves it and goes to a different one. Covalent bonds, the electrons are shared. So this sharing is what holds the covalent bond together because they both have access to the electrons. So something like water, H2O, that's a covalent bond. And hydrogen and oxygen both have access to the electrons. They're not transferred. They both have access to them. Metallic bonds are a little bit different. In a metallic bond, electrons are delocalized. And this delocalization of electrons sometimes has its own specific name, and I just want to jot that off to the side. So this delocalization, sometimes you will see this called the electron sea, or a sea of electrons. So the electrons are kind of roaming around free and anyone can use them. Any of the metals are welcome to them. So the type of element in that bond will tell us a lot about it. An ionic bond always forms between metals and non-metals. And if you remember, metals always form cations and non-metals form anions. So when we have an ionic bond, we're dealing with ions there. To remember ionic metal and non-metal, I like to remember the little phrase, I love M&Ms, because it's I for ionic, love, and then metals and non-metals, M and M's. So hopefully that helps you. I love M&Ms for ionic is between metals and non-metals. Covalent, they are between 2 or more non-metals. And metallic bonds, as it sounds like, they are between metals. So an example of an ionic bond that we were talking about was NaCl, sodium chloride, table salt. Na is our metal, Cl is our non-metal. We have an ionic bond. I mentioned H2O as a covalent bond. Those are both non-metals, hydrogen and oxygen. Another covalent bond you'd be familiar with. Take a nice deep breath in and out, and as you breathe out, you release CO2. That would be a covalent bond. They are both non-metals. Another one, let's say you had some sugar at some point in time today, C6H12O6 sugar, that would be a covalent bond as well. Other examples of ionic bonds, we could have potassium iodide, or we could have calcium oxide or lithium nitride. There's lots of examples there. And for metallic bonds, we're just looking at things that are metals like copper or chromium or something like that. Let's discuss the different properties they each have. You noticed on the simulation that as you put salt in water, it became electrically conductive. So ionic bonds are really special that when they dissolve in water, they make electrolytes, which means they can conduct electricity. And electrolytes are super important. You know that as you sweat, you release salt, and those are electrolytes. So after you've done a lot of running or you've worked outside for a long time, you've done a lot of sweating, you start to feel really drained. And then maybe you drink something like Gatorade, or you have some other sports drink, or you add electrolytes to your water. Now you start to feel better, and that's because electrolytes conduct electricity. And your body has to have that in order to function. And we know that there's an electric current passing through our bodies. And so that comes from different types of ions. And you learned about ion pumps and that sort of thing in biology, but we have to have those, and they come from ionic bonds. Something like sodium chloride in your food dissolves in water and then helps your body function. Other properties of ionic bonding. Ionic bonds are really brittle. They're really fragile, easily broken. Think like a really thin cracker. That would be really brittle. Or like a bag of potato chips. Very brittle. Ionic bonds also have a high melting point and boiling point. So it takes a lot of heat, a lot of energy input for these to melt. Let's talk about covalent bonds. So covalent bonds, they're a little bit weaker than ionic. Ionics, these are the stronger bond, and covalent's a little bit of a weaker bond. Covalent bonds have lower melting and boiling points than ionic do as well. Lastly, we have metallic bonds, and this is where you think of typical metals. Metals conduct electricity. They're also great thermal conductors. Metals are malleable. They're very ductile as well. And all of these really great metallic characteristics you think of, that will go for your metallic bonding. Up next, we have electronegativity differences. So you've learned about electronegativity in our previous units. So electronegativity is the tendency of an atom to attract electrons. So looking at the periodic table, let's look at metals versus nonmetals, and then some electronegativity differences. So metals are to the left of that staircase. All of these that are highlighted here are metals. Metals have certain electronegativity values, so do nonmetals. So because of the electronegativity value, we can look at the elements in a bond and figure out the differences in their electronegativities and then classify them from there. So if you have an electronegativity difference that is greater than or equal to 1.7, you're going to have an ionic bond. Covalent bonds, we are going to divide into two categories. And the first one is a polar covalent bond. We'll talk more about what that means in a little bit. And a polar covalent bond is going to be the values 0.3 to 1.7 of electronegativity differences. And the other type of covalent bond is called a nonpolar covalent bond, and they have an electronegativity difference of less than or equal to 0.3. And then this is not applicable for our metallic bonds, so you can just scribble that out or draw a little doodle in there if you would like to. So we're going to do some practice with these then. Up first, let's practice just identifying the type of bond based upon the element inside that bond. And then in a little bit, we're going to talk about the formation and then look at those electronegativity differences as well. So let's classify these 5 different compounds. Let's do the first one together. Number 1, CaCl2. On a periodic table, we can find Ca. Ca is number 20. It's on our left side. That's a metal. Cl is on the right side. That's a nonmetal. So we have a metal and nonmetal together. A metal and nonmetal together tells us we have an ionic bond. So this first one would be an ionic bond. Try the other ones on your own, and then let's go over the answers. SiO2, this one is a little bit tricky because silicon, a metalloid. So because of that, it's a little bit tricky, but this one does turn out to be a covalent bond. N2O4, this one was a little bit easier. This one is definitely covalent. Nitrogen and oxygen are both non-metals to the right of that staircase. Next, Cr, chromium, that would be a metallic bond. It's just a metal. And then lastly, HgCl2. Hg is a metal, chlorine is a non-metal, so we have an ionic bond. Next, let's talk about how these bonds form. So right here at the picture, we are looking at sodium chloride. From last unit, you learned Lewis dot diagram. Sodium has 1 valence electron, and chlorine has 7 different valence electrons. Both of these want to become stable, and you know that sodium typically forms a 1+ ion, and chlorine typically forms a 1-. But here's why. When these form a bond, sodium's electron gets transferred to chlorine right there. When sodium loses its electron, it forms a positive charge. It lost an electron, so it's a positive ion. Chlorine has now gained an electron, so it's a negative ion. The attraction between the positive and negative charge here holds the bond together. And it's this transfer that results in the ions. And that's why these pair up, because sodium has 1 electron to get rid of and chlorine needs 1 more electron. So it's this perfect match. Sodium gets rid of its electron and it transfers it to chlorine. The ions form, and now this electrostatic attraction holds them together. Let's finally talk about our 2 different types of covalent bonds. There's a nonpolar covalent bond and a polar covalent bond. So in a nonpolar bond, electrons are shared equally between 2 atoms. And in a polar covalent bond, electrons are shared unequally. So because it's covalent, both of these are going to be sharing electrons, right? We see this shared is similar on both of them, but it's how they're sharing it that makes a difference. So we can see on the picture here that we have this very equal distribution of electrons. We see these yellow electrons from this chlorine and these orange from this one. Here in the center, there's an electron available to both of them. So this chlorine on the left has access to the yellow and orange one. This one has access to the yellow and orange as well. They're equally sharing all of the electrons. Because of that, we see this very uniform distribution. The electrons aren't gathering in one place over the other. They're staying very equal. In a polar covalent bond, however, we are sharing unequally. So what happens is that while hydrogen has access to the yellow and orange, and this chlorine has access to yellow and orange, the electrons tend to spend more time around chlorine. We see there are more valence electrons here, and chlorine is more electronegative than hydrogen. So because of that, we see this unequal distribution of electrons. In this blue region here, electrons are spending more of the time, which creates this sort of pole. And that pole is represented by this symbol. This is the Greek letter delta. It's a lowercase delta. And that stands for this partial charge that is induced from these sort of unequal electronegativities here. Chlorine is very electronegative, so the electrons are there more frequently, which makes this a negative charge. Hydrogen, the electrons are spending less time around there, so we get this partial positive charge. So a pole is induced because of the unequal sharing of electrons. So we call this a polar covalent bond because of that. In order to tell if something is polar or nonpolar, use your electronegativity differences. we can look at the electronegativities on the periodic table, do a quick calculation. You'll learn how to do that in just a minute. And then you can tell based on that if it will form a polar or non-polar bond. Let's talk about metallic bonds and how they form. So this formation of bond, we can see that these positive charges are here, and these are the nuclei of the metal atoms. So this metal ion, and it is in a fixed position. They are not moving. However, these delocalized electrons, the blue dots here, they can move freely around. And that's how a lot of the properties of metallic bonds occur. Because these electrons can move freely around, we can conduct electricity, they're more malleable, and we really see the properties because of how delocalized they are. You know the trend for electronegativity. We're least electronegative by francium, most electronegative by fluorine. We can look at the electronegativity values to figure out what type of bond is being formed. We're going to do the first couple together, and then you're going to try the others on your own. So number one, if we have the bond H2O, we can tell that this is going to be a covalent bond. We know that we have the staircase right here, and we have metals on this side and non-metals over here, except hydrogen is the exception. It's also a non-metal. We know it's covalent, right? We've got hydrogen, oxygen, both non-metals, but we don't know what type of covalent bond it is. We can do a little math though and find out. Hydrogen's 2.1, oxygen's 3.5. Let's just do a little subtraction, find out the difference. 3.5 minus 2.1, it's 1.4. So now we can go back up to our notes. 1.4, that is in the polar covalent range. So water is a polar covalent bond. So this would be polar covalent. Let's do number 3 together, and you can try 2 and 4 on your own. So number 3, we're looking at iron right here. And once again, we're looking at oxygen up here. Iron has an electronegativity value of 1.8. Oxygen has a value of 3.5. Let's do a little subtraction, figure it out. 3.5 minus 1.8, and it's 1.7. So this is an ionic compound. Go ahead and try number 2 and number 4 on your own, and then unpause the video for the answers. Okay, for number 2, we have Na is 0.9. Chlorine is 3.0, so if you have 3.0 minus 0.9, you have a difference of 2.1, which means this one is an ionic compound. Number 4, P and Cl. P is right here, Cl is right here. 3.0 minus 2.2 is a difference of 0.8. So if we check our list for 0.8, a value of 0.8 would give us a polar covalent bond. So this one is polar covalent. One other quick thing I want to mention, a lot of times you hear the word molecule thrown around, and a lot of times it's used synonymously with the word compound, and that's not the case. Only covalent compounds are considered to be molecules. So what we see is that all molecules, all covalent bonds are compounds. However, not all compounds are molecules. Only some compounds are molecules. So use the term correctly. You now know covalent bonds are molecules. All right, to recap, you know that atoms form bonds to become stable. You know the 3 types of bonds, how they form, the elements. You know the properties of them, the electronegativity differences. You can look at just a compound to figure out, is it ionic, covalent, or metallic? You know how they form. We can see the transferring of electrons, whether or not the electrons are shared equally or unequally. And then you can calculate the electronegativity differences to figure out what type of bond you have. That is it for your chemical bonding notes.